Hey y'all, so my hope this morning is to help get you a little bit more comfortable with centripetal force and centripetal acceleration. We've already talked about the idea in class that anytime an object is going with a constant speed in a circle, or part of a circle, right, with constant radius, constant speed, we call that uniform circular motion. All right, now what we've talked about is the fact that an object doing that is accelerating, and the acceleration is always towards the center. And so we talked about the fact that that force, or the piece of the force, or the combination of the forces that are towards the center is what we call the centripetal force. Now, the big idea that I want you to get from this video is that the centripetal force is not a new force, right? It is a label that we give to the force, or the forces, or the pieces of the force that are the net force towards the center of the circle. All right. Now, one of the things I want to do before we get into some problems and some conceptual kind of discussions here, and do keep in mind that even though we're working through problems, the hope is that we're understanding these situations conceptually, is I want to introduce to you the equations for centripetal acceleration and centripetal force. Okay. Now, I'm not going to go through a proof or anything like that for this, but centripetal acceleration is simply A equals v squared over r. Now the v here is not velocity, okay? It's just the speed, right? Because it is going in a constant speed around that circle, okay? So we are using the v for speed, v squared, over r, which is the radius of the circle, or the radius of the circle if you were to complete a whole circle. And then a is the magnitude of the acceleration. So we're just working with scalar numbers here. We're not working with vectors. We know that the direction of our acceleration is towards the center. And so you can't really give a direct, you can say towards the center, but other than that, you can't really give a direction unless you know the exact location of your object on the circle, because then you can show that it's at this angle or it's horizontal or whatever else. Okay, but it is always towards the center. Now, this will be very important as we go forward. The other thing is centripetal force. Now, acceleration is often given to you in a data booklet or a formula packet, but very often they don't give you centripetal force. What you have to remember is that the sum of the forces is equal to ma, right? The net force causes the acceleration, okay? Now, if the centripetal force is the net force, then it is causing the centripetal acceleration. In other words, if the sum of the forces is the centripetal force, right, which again, it might be a single force, like in class we did the tension as the minion was going horizontally around my head. When the string was at an angle, it was just the horizontal component of the tension, right? So whatever the centripetal force is, and we're going to find some situations next class where sometimes the centripetal force is a combination of forces as well, okay? So centripetal force is the sum of the forces, which is going to equal m times the acceleration, which if the centripetal force is the net force, then the acceleration is v squared over r. And very often you'll see it just written as mv squared over r. Again, recognize that v is just the speed, r is the radius of your circle, and then m is the mass of the object that's actually making the circle, right? Not the one in the center causing it, but the mass that is actually traveling in a circle. All right, so with these things here, we're going to go ahead and start looking at a couple of other questions and see what we can do. All right, so I'm going to scroll up. This first example is not in your notes packet. I've added it in because this is similar to what we did in class, and I felt like it might be valuable for us to look at something a little more similar first, and then we'll look at some different situations, all right? So a child is swinging a toy airplane with a mass of 450 grams. And the first thing I see when I see this 450 grams is, no, I don't want 450 grams. I want 0.450 kilograms. So 450 grams around in a circle. Assume that the circle is nearly horizontal. Okay, so circular airplane being swung around by a string. Now, the reality is that the string can't ever be perfectly horizontal. because gravity's pulling down, so therefore the string has to pull up just a little bit to balance gravity. However, in this situation, we're going to say it's nearly horizontal, so we're not going to worry about the vertical forces at all. All right, in a later question at a later time, you may be asked to consider that situation more like what we saw in class with the minion that was swinging around at an angle. And when that was the case, we had to only pay attention to the horizontal piece. So hopefully we'll get into that a little bit later. But for now, we're assuming that the circle is nearly horizontal for our first question. Okay? If the plane completes a full circle every 0.89 seconds, and the length of the string is 1 meter, determine the amount of tension in the string. All right? Now, what we're looking for then is the force of tension. Okay, now I'm going to label it this way, FT. Sometimes we've just put a capital T, but one of the things here that they've given us is it says the plane completes a full circle every 0.89 seconds. We defined that in class. We said that the time it takes to complete one full circle is what we call the period. And the period also uses a capital T. And so my period is 0.89 seconds. All right? So I'm going to use capital T for the period. I'm going to use F of T for the force of tension. So that's what I'm looking for. Now the big thing here, almost I would say 95% or more of anything that has circular motion or part of a circle, right? A hill with a constant radius, a curve with a constant, anything that's almost circular or circular in nature, you're probably going to be asking yourself, what is causing my object to go in a circle? And by that we mean, what is the force that's making it so your object doesn't go in a straight line? Right? If the object goes in a straight line, then we know the forces are balanced. The fact that it's not going in a straight line must mean that there's a net force. The fact that it's keeping constant speed, constant radius, must mean that there is a centripetal force. So the question here is, what is the centripetal force? And as we know from class, the centripetal force here is the string, the tension, right? That's what's pulling towards the center of the circle, causing the airplane to go in a horizontal circle. So I'm going to write down that the force of tension is the centripetal force, just like that. So the force of tension I can't solve by itself, right? What I can do is I can solve for the centripetal force. We just on the previous piece of this video said that the centripetal force is equal to mv squared over r. Remember that in the database, in the data packet, in the formula packet, it very often only gives you A. You have to remember that force equals m times A. So therefore, the force of tension is equal to mv squared over r. The mass is given to us, right? 0.45, so we got that one. The r is given to us 1, but they haven't given us the speed, right? And so we need to actually find that before we can answer this question. And so we're going to kind of go to the side and think for a little bit. Well, what other information do I have? I know that it completes a full circle in 0.89 seconds. So from here all the way around the circle, the time is 0.89 seconds, the period. Now, if only I knew how far it traveled in that amount of time, I could simply go speed equals distance over time. Oh, well, I can figure that out, right? Because I know the radius. The radius is 1 meter. And knowing that the radius is 1 meter, I can then find the circumference of the circle, and that's the distance that it traveled in one complete circle. So I'm going to find the circumference, which is 2 pi r. All right? So this equation right here just becomes the distance, which is 2 pi r. It completes one full circle in that period, which is t. And so now we're just going to take that, we're going to plug it into our fancy smancy calculator here. And so we're going to go 2 times pi times the radius. The radius was 1, so I'm going to go ahead and put in 1. And then I'm going to divide by 0.89. And I get a velocity, speed, of 7.059. So I'm going to go ahead and write that as 7.060. It's 597 I'm going to try to keep a couple extra digits, so I'm going to round it to 7.060. Now, if I do any calculations later, I'm going to be using the full number on the calculator anyway, but just for my mental capacity, just in case I lose what's on the calculator, I can always come back to this number, and I have a couple extra digits. Now, what do I mean by extra digits? We haven't looked at this a lot in class. However, we're going to start trying to think about it now that we're starting to get a little bit more comfortable with the physics. Notice that in the question, the 450, we would say this has two significant figures. Okay? The 0, this could have been rounded to 450. We don't know. And so therefore, we would say only 2 of those are significant. We notice that the distance is 1.0, 2 significant figures. The time is 0.89, 2 significant figures. So all the data that's given to me has 2 significant figures. So my answers will all have 2 significant figures. Okay, we'll talk more about that later, like I say, but I'd like to start kind of thinking about that. So really, when I give final answers here, I only want to have it in 2 significant figures. This would be 7.1, right? But in the middle, I want to make sure that I'm keeping some extra digits just to make sure that I don't round and round, right? If I round and then round again and then round again, and eventually I've rounded and I get an answer that's completely wrong because I've rounded so many times. So I'm going to try to avoid that. So anyway, we now go back into the force of tension here. We're going to use what we just found. The mass, which we know is 0.450. The speed, which is that 7.060. I'm going to use the full number that's on my calculator and then divided by the radius, which is 1. And so if we go 0.45 times our answer squared and then divided by 1, and we get that the force of the tension is 22.4 newtons. Okay, now everything was in SI units, so I know it's in newtons. My final answer, though, will be 22 newtons because that is 2 significant figures. All right? Now, that's part A. We found the tension in the string. Now what I'd like to do is let's go into letter B. In letter B, we're now finding it says the string will break if the tension is greater than 50 newtons. What is the maximum speed that the plane can travel? So this is kind of the backwards, right? This is kind of the opposite of what we just did. The force of tension is still the centripetal force. And so I'm still going to have this idea of, this is part B, the force of tension is going to equal mv squared over r. So what I want to find is the biggest speed that my plane can travel and yet not go over 50 newtons. If I go over 50 newtons, there's too much tension, the string's too tight, and the string will break. Okay? So I'm going to find the limit. The way to do that is by putting 50 in for tension, right? Then the mass, which is 0.450, the velocity is what we're looking for, and then divide by the radius of 1. Obviously, any of these numbers can change in this second part, but in this situation, we're keeping everything else the same. So therefore, we're going to take the 50, we'll multiply it by 1, then we're going to divide by the 0.450. That's going to give me 111.11. That's going to be equal to v squared. And so then I'm going to square root each side. So I'm going to square root the answer here. And my final answer is that my speed can be anything up to 10.5. So it's 10.5, but because I'm doing 2 significant figures, I'm going to say 11 meters per second. And so that's the maximum speed. Notice that that's faster than it was traveling before. It's not double, right? A lot of students would be like, oh, well, 22 newtons, I just need about double that. And no, that doesn't work because the speed here is squared. There's a quadratic relationship. All right? So we end up getting 11 meters per second for the maximum speed that that airplane can be traveling. All right? Not too bad, right? Not too bad. Again, the idea is recognize what is the centripetal force and work with what you have and what you need from there. All right? So let's go ahead. Let's look at a different question now. We're going to look at example number 20 from your packet. So this actually is in your packet. I'm going to get rid of everything here. Don't worry. I know some of you are like, wait, I'm erasing. No, you can rewind the video. It's okay. Okay, it's all right. It's all right. Just rewind the video if you need to. Otherwise, I'm just going to erase everything up here on the board, and we're going to start again with a new question. All right. This is a very typical type of question. We have, sorry, so this is a different kind of idea. Sorry, the next one is the typical one that you often see on exams because it combines so many ideas. This one hopefully is a little bit more straightforward again. The Earth has a radius of 6.4 megameters. That's 6.4 times 10 to the 6th. If you didn't know that, you can look it up in your data booklet, in your formula packet. It says that the M is the metric mega, which is 10 to the 6th. So 6.4 times 10 to the 6 meters. Determine the centripetal acceleration experienced by someone on the Earth's surface at the equator. Okay, so we know that the Earth is a sphere. The Earth rotates around like this. Somebody on the surface is going on a circle around the center of the Earth. Okay, now you don't have to worry about all the individual forces. The fact is the person is going in a circle, therefore the net force is towards the center of the circle. If not, your person would not go in a circle. Okay, now what are the forces on the person? If you think about that, well, it's gravity pulling towards the center of the Earth, and it's the normal force pushing out. And so, generally speaking, we say that the force of gravity and the normal force on a person are equal because they're maintaining their state of motion. Well, technically that's not true because they aren't staying still. They're actually going in a circle around the center of the Earth, which means that one of those two forces has to be bigger, right? The force towards the center of the Earth has to be larger than the normal force. That way there can be a net force towards the center of the Earth. Okay? Think about that. If you didn't quite get that, rewind it and listen to that again, right? A person on the surface of the Earth, actually the forces are not balanced. You've got the force of gravity and the normal force, like this. But if those two are equal, the person would go in a straight line and they would leave the surface of Earth. The reality is the person is accelerating towards the center of the Earth as they're going in a circle around the center as the Earth spins. Therefore, the downward force must be slightly larger than the upward force. What we're going to find right now is how much larger, how big of a difference. Have we really been messing things up, or is it close enough that we can say that the difference is negligible? All right, so that's what we're going to look at right now. So we are saying here that we have, we're looking for the centripetal force, right? Actually, we don't even need the centripetal force, do we? We need the centripetal acceleration. So I'm gonna say, nope, not centripetal force. We actually want centripetal acceleration here because that's what it's asking us for. What is the centripetal acceleration? And we know that that is equal to v squared over r. Now, I do have the radius, right? That was given to me. But I don't have the v squared. I don't have this speed. So again, I'm going to have to kind of think outside the box a little bit and see if we can find the speed. Now remember in the previous question what we did is we knew the distance that the airplane was traveling, or we could calculate the distance it was traveling, and we divided by the amount of time that it took it to do that, right? So we just said speed is equal to distance over time. Well, you know what? We can do that here too, right? We can take the distance, which is 2 pi r. We know the radius of the circle, right? We're talking about somebody on the equator, so the radius of the circle is the radius of the Earth. Okay, we know that. And then the time, how long does it take them to go all the way around the Earth? It takes them 24 hours, right? 24 hours to go from one point all the way around, full day, rotate to the point they started at. All right, so 24 hours. Now, the 24 hours, I don't really want hours, right? Hours is not helpful to me here. I need it in seconds. I need it in SI. So I'm going to take the 24 hours. I'm going to multiply by 60, and that will tell me how many minutes there are. And then I'm going to take that and multiply it by 60 again, and that will tell me how many seconds there are, right? I should get a big number. There's a lot of seconds in a day. So I'm going to take the 24 times 60 times 60, and I get 86,400 seconds. All right? Now that's an exact number. right? That's not an estimate. We definitely didn't round those numbers. And so this actually is 5 significant figures. We were talking about significant figures before. The zeros are only not significant if we don't know if it was rounded or not. Okay, this one we know for sure that I didn't have to round to get that number. So all of those would be considered significant. All right, so we are going to go ahead and do the distance, which would be 2 times pi times the 6.4 times 10 to the 6th, and then I'm going to divide that by the 86400. So let's do that. 2 times pi times 6.4 e to the 6, and then I'm going to divide that by 86400, and I get that my V is 465.42 meters per second. Holy smokes, really? Yeah, that's how fast you are traveling in a circle around the center of the earth. But the speed is not important. You cannot feel speed unless you're out in the air where the air is pushing against you. But on the surface of Earth, the air is moving with you. You can't feel constant speed. What you feel is acceleration. If you are accelerating, you can feel that because acceleration is caused by a force, and you can feel a force. If there's no net force, you can't feel the change. You can't feel whether you're faster or slower. The only way you know is by looking out and seeing other things, by feeling other things hitting you. That's the only way you can know if you're going fast or slow. Try it next time you're in the car. Close your eyes. You might be able to tell by the bumping of the car, but otherwise you won't be able to tell how fast you're going when your eyes are closed. It's true. It's true. All right, so now we can go back into this. We're going to go centripetal acceleration is equal to the V, which would be that 465.42 squared, divided by the radius, which is still that 6.4 times 10 to the 6th. So I'm going to take my answer, I'm going to square it, I'm going to divide by 6.4 times 10 to the 6th, and I get that my centripetal acceleration is 0.03. So I have 2 significant figures there. So you always go with the least number of significant figures that you had available in your data. And so 2 would be it here. And so I'm going to go 0.34 meters per second squared. So notice that the centripetal acceleration of you going around the center of the Earth, because the Earth is so large, yes, you're moving fast, but the Earth is so large that you really aren't going to feel anything at all, right? Compared to the 9.8 that is the force of gravity, this is minuscule, right? It's so small. It's like 1/3%. It's so small that we would then consider it to be negligible. So don't worry, all these things we did before about saying the normal force and the gravitational force are approximately equal, yeah, you can still do that. They're still pretty close to each other. All right? There we go. That's that question. Okay? Now, let's move on to another. This next one I'm a little bit excited about. Actually, I'm excited about pretty much everything physics. But we're going to go on to the next one. And I want you to see, this is a very typical type of question. Not necessarily because of the topic, but because it combines several different ideas of what we've done before. Okay? So we have a car that is exiting the highway. Okay? The car, 1,200 kilograms, goes, now this is 2 significant figures. We don't know if that was rounded or not, so 2 significant figures. Goes through a turn of radius 50 meters. Now this is only 1 significant figure, right? We don't know if that 50 meters is actually 50, if it's 51 meters and it's been rounded. We don't know. So therefore, that's really only 1 significant figure at a speed of 45 miles per hour. And that's already been turned into meters per second for us. Again, 1 significant figure. Okay, so as we write our answers later, we are going to try to put it in 1 significant figure. All right, so the question is, assuming that the road is flat, what force of friction is necessary to keep the car on the road? We talked about this in class, right? We said as the car goes around a circle or a part of a circle, right, the radius here is 50 meters. That's the same at any point towards the center. We do know that the speed at this point is 20 meters per second. They did that for us. They might not give that to you, but generally speaking, IB at least is pretty good about giving you meters per second, not having to go back and forth. They might give you kilometers per hour, right? But they probably won't give you miles per hour and have you go cross systems, okay? They'll probably give it to you in SI. You might have to deal with the prefixes, you know, kilo and milli and that kind of stuff, but you probably won't need to go back and forth between miles an hour. But I am comfortable with miles per hour, so that's how I ended up writing the question. So assuming that the road is flat, what force of friction is necessary to keep the car on the road? So just like in the previous questions, one of the first things that you want to do is you want to say, okay, the car is going through circular motion, right? We know it's circular motion because we have a constant speed, we have a constant radius, so therefore that's uniform circular motion, even if it doesn't complete a full circle. Now at this point we say, all right, well, if it is going in a circle, why? Why is it going in a circle? Why is it going in circular motion? Well, the answer is, and we talked about this in class, friction, right? If there was no friction, you could turn the steering wheel all you want, but your car would continue to just go in a straight line. So therefore, the net force is going to be towards the center, and it's going to be friction, okay? Now, we also understand that there's probably friction between the tires that's causing your car to go forward. There's probably some friction and resistance inside the car. There's probably some air resistance. There's a lot of other forces, gravity, normal. There's a lot of other forces involved here. But when you put all of those forces together, the net force must be towards the center of the circle. That's it. The net force must be towards the center of the circle. So, therefore, what that means is that the force of friction is the centripetal force. You should do this simple equation right here. Anytime that you see something in circular motion, if it says it's a constant radius, any of those things, you should be looking for what is the centripetal force. Okay? Now I know that some of you are thinking, I know that force of friction is equal to coefficient times the normal force. I can get normal force because the normal force is equal to the force of gravity, and then I don't know the coefficient of friction. You're right, you don't know the coefficient of friction, so we can't use that yet. Okay? Notice that the last question, C, does ask what is the minimum coefficient of friction. So we are going to find that. We are going to use that, but we can't use it now. So instead, like I said, if it's circular motion, chances are this is what we're looking at. So the force of friction, therefore, needs to be equal to mv squared over r. We have the v. That's given to us, right? It gives us the speed, 20 meters per second. It gives us the mass. We've got that. And the radius. That's given to us too. So really, this is easier than the previous questions because all we have to do is put in our mass times the speed over the radius, and we get the answer. So I'm going to do that. Why don't you do it? Here we go. We got 1,200 times 20 squared, and then divided by 50, and we get that the force of friction must equal 9,600 force, so newtons. Now, as an answer, remember I can only have one significant figure. So I am going to write that down, but in the end, when I write my answer to letter A, I need to write one significant figure. That would be 10,000 newtons. Okay? Now I am going to write this down just because that will be easier for me later if I need that number. I can go back to this number and I can use that. Okay? Now, so that's it. That's part A. Piece of cake, right? Letter B then says, is static or kinetic friction? The static, remember, is when the object is at rest, not sliding on the surface. And kinetic friction or sliding friction, sometimes we call kinetic friction sliding friction, that's when the two objects are sliding. Okay? Remember that kinetic means sliding. It doesn't necessarily mean that the object isn't moving, right? Because right now that's the question, is it static force or is it static friction or kinetic friction? Well, when it comes down to it, is the wheel sliding on the surface of the road as you're turning? And the answer is no, it's not, right? As the wheel turns, the point of the road the point of the wheel that is on the road isn't sliding. That's always kind of at rest in that instant, right? In the next instant, it's already rolling, it's already going somewhere else. But that point right there is in contact with the road and not sliding. So therefore, which type of friction is it? It is static friction. Now, static friction is stronger than kinetic friction. That's why when you watch movies or whatever, you see cars, they're making a turn, and as soon as they start sliding, they're done for, right? Because the kinetic friction, the sliding friction, is not as strong as the static friction. So as soon as you start sliding, you're likely going to keep sliding until you get to a certain point where the static friction can kick in again. All right, so next question, what is the minimum coefficient of friction necessary here? Okay, so now this is where we're going to step back into the formula that we know. Now, we know the force of friction now, which I'm going to put in the 9,600. I need to know the normal force. So to get the normal force of the car, we're going to go back to the car, which is on the road, right? We've got the force of gravity down, and we've got the normal force up. And because the car is not accelerating up or down, these two forces must be equal to each other. And so the normal force has to be equal to the gravitational force, which then is equal to mg. And so I can put that into my formula now. I'll put the force of friction in, which is 9,600, the coefficient, and then the normal force, which is the mass, 1,200 times 9.8. Okay? And now I should just be able to put that in. I can take that 9,600 and then either multiply the 1,200 times the 9.8 and divide, or divide by the 1,200 and then divide by the 9.8. Doesn't matter. Either way, what I get is 0.8163. Okay? Remember that coefficient does not have units because it's in comparison. It's connecting these two. This is in newtons, this is in newtons. If that had units, these two sides wouldn't be equal anymore. It just is a ratio of how much friction is there based off of a normal force. Now, the reason why the question says, what is the minimum coefficient of friction, is that remember with static friction, it could actually have a higher coefficient than this. You could have a 0.9 coefficient. That means that there's more friction available. Remember with static friction, this formula tells you how much friction is available. It doesn't tell you how much friction there is, right? In class, we gave the example of somebody sitting on a chair. If you just push them slightly, like you barely touch them with their finger, they don't need very much friction to stay at rest. And so they're not going to have this whole amount of friction. As you push harder and harder, the amount of friction between them and the ground has to increase and increase as you push harder and harder. And so this formula for static friction gives you the maximum amount of friction available. It does not tell you how much there is in the moment. And so that's why this 0.8163 is the minimum coefficient. Anything higher than this will allow me to have a higher friction, which means I could technically be going a higher speed, right? I do want to remember that I'm supposed to be putting one significant figure here, so my final answer is going to be 0.8. All right? Now, as you'll find out in the next question, the next piece of the question, 0.8, 0.7 are actually fairly common coefficients of friction between tires and ground, which means this is probably pretty close to the limit. So this is where you might see a sign on the side of the road. It probably would not say that the speed limit is 45. It would probably say the speed limit is 35 because they know there are always idiots that are going to go over the speed limit. And so they'll put a speed limit sign there saying, well, we know that 45 is the absolute maximum speed with this coefficient. Therefore, we're going to tell them to go 35. And therefore, if anybody goes a little bit over, they're not going to skid out. Because anything over that, anything over the amount of friction possible, you are going to skid and you're going to fly off the edge of the curve. Okay? Now, we're almost done. We're almost done. I do want to look at example number 22 here. The numbers might be different in your notepad. The number of the example is not important. What is important is the concepts, obviously. So the road in example 21, so same road here, so I am erasing it, but you can always look back up at the previous question. You can always rewind the video if you need to. So same road, but now it's covered in ice. Because it's covered in ice, there's negligible friction. And remember, I shared my story with you about driving in the snow late at night, and I was driving, got up to the stoplight. I slowed down. I wasn't going very fast, and I turned my steering wheel, but because there was ice, there's actually probably a patch of black ice, which that makes it so that you can't see it very well. Because there was ice, I had no friction between my tires and the ground, and so therefore when I turned my tires, my car didn't turn. My car just kept sliding straight through the red light. And luckily it was very late at night. There weren't any other cars. But it was a very scary experience to know that I had zero control over the situation. The car was sliding. There was nothing I could do about it. All right? So the road in example 21 is now covered in ice, meaning that there will be negligible amount of friction. At what angle should the road be banked so that the car will not fly off the road? And we did mention this in class. Right? We did talk about the fact that you could bank the road, and sometimes they bank the road because now it adds in some more force towards the center of the circle. And if you add more force towards the center of the circle, then you can go faster, right? The centripetal force equals mv squared over r. So if you increase the centripetal force, you can increase the speed of your car as well, right? So the idea here is I'm going to draw a picture looking from the rear, looking from the back of the car. So this is the car right here, okay? There are the tires. You can kind of see the tires on the side. The car is driving into the page, so it's going around. So maybe it started here and it's going around like this, right? The slant of the road is meant to help us a little bit, right? So if we look at the forces, if we draw in the forces in our free body diagram, really, the only forces that we have are the force of gravity downwards and the normal force upwards. Now, in a normal situation, you could actually have friction here as well, right? Because the car would be trying to slide down the ramp, so maybe there's some friction up the ramp that's also holding the car up, right? In this situation, we don't, because it clearly states that because of the ice, there is no friction, right? So that'll be helpful to us in solving this bit of the question. Okay? So we've got these two forces. We know that the car is going in a circle, which means that the net force or the centripetal force must be towards the center of the circle. That means that all the vertical forces have to balance out, right? The vertical forces have to balance out. So if I draw in the component of my normal force, okay, the normal force, the vertical part of the normal force must be equal to the force of gravity. Otherwise, my car would be slipping up and down, not just turning. So I know that the verticals are the same. So this right here must be Fg, which Fg is mg, which, remember, it was 1,200 kilograms times 9.8. So that's got to be the vertical part. Now, secondly, we have the same car, right? Same car, which is going at the same speed as before, around the same curve, same radius, which means we need the same centripetal force to get it to go in that circle. Now, what that means is we need the same amount of friction to go in that circle, right? So this number right here, that is the centripetal force. That is the force going towards the middle. That's the centripetal force, and that's going to be the same thing that it was before, right? If you don't believe me, you can go ahead and write it out. Centripetal force equals mv squared over r. Your mass is the same, your velocity is the same, and your radius is the same. It's all the same, right? We know that the centripetal force then needs to be that 9,600 that we had from the previous one. And so you've got a vertical force of 1,200 times 9.8, and you've got a horizontal force of 9,600, which means we can figure out what the angle of the slant is, right? So the theta we're going to go tangent, opposite over adjacent. Okay, so tangent of theta equals 9/600 over 1200. And we can go ahead and solve that. That's just inverse tangent, because I'm going to do the inverse tangent over the other side, of 9/600 divided by, it's 1200 times 9.8. And I get that theta equals 39 degrees. And again, if I'm still going with the whole one significant figure thing, then I would write my final answer as theta equals 40 degrees. Now, just in case you're saying, but is that really the angle that I want? You should be asking that. Please remember that the road used to be flat. So if the road starts at flat and rotates up that far, then that is the angle of the bank, right? From here to there is the angle of the bank. The normal force when the road was flat was straight up and down, and as the road banks, the normal force rotates over this direction. And so you can see right here, that was the original direction of the normal force, and it's rotated over in this direction, the same angle that this has been rotated up. There's other ways to show that mathematically, geometrically, but hopefully that kind of makes sense. This rotation must equal that rotation because the whole thing is rotating over this way at the same time. And so we end up getting that angle right there is the same as the angle of the bank. All right? So that's it. That's it. I would like for you to try example number 23 on your own. The next one, whatever the next one is in your notes packet, try that one on your own. Okay, for those that don't have it at home, I'll try to put it up here. There you go. Okay, so this is the next question. This is similar in some ways, but approaches it from kind of a different angle. All right, so hopefully this, I'll post up an answer key for this. You can check it with your homework, and I hope that it'll be straightforward given the types of questions that we work through here. We'll continue to work on this in class, but this will give you a very good introduction to what we're hoping to get as we look at things going in circles. Circular motion, centripetal force, centripetal acceleration. We'll see you next time.